Hey everyone, it's George from SkyCiv here. Today I'm going to be running through one of the new exciting additions to our Quick Design library, which is our AS2870 Residential Slab Design module. Now this module is intended for the design of stiffened raft slabs in accordance with the Australian Residential Slab Design Code, and it follows the simplified method specified in clause 4.5, which allows you to deviate from the deemed to comply designs in that code and specify your own beam arrangement and reinforcement detailing. So we'll start off by setting up the dimensions of our slab here. Using these inputs, you can see we've got a drawn interface here. And you actually export these drawings using the graphics PDF button here on the right-hand side. Now we can set up a custom beam arrangement here as well, just by inputting the number of beams in each direction. And you can customize the depth of the width of the beams here as well. So reinforcement is specified in these inputs here. We can specify top and bottom reinforcement if we want to, but we can also remove it if required from the top of the beams and only rely upon the slab mesh that runs through the beam there instead. Now for loading inputs, the first input is the wall construction of the house that's been built on this slab. And this varies from full masonry to clad frame. And this really is an input into the deflection requirements for the slab, but also for the maximum beam spacing. And this is pulled from figure 3.1 in the code. We carry out a deflection check based on the values obtained from the code, and you can customize how this is done. You can either check the limit, so the millimeter maximum deflection, or you can check a span ratio as specified in table 4.1, or you can check both if you'd like to as well. We've inputs here for distributor load and edge line load. And they're not used necessarily for capacity calculations, but they're used because there are limits in clause 4.5 on the maximum allowable distributed and edge load on your slab. So this is just a quick check to make sure that we're within the limits and the simplified method is applicable. For the geotechnical parameters, you'll specify the moisture change in the soil as either normal or as deep-seated. And this is used for the stiffness calculations later in the report. And you choose a different curve on figure 4.1, depending on whether your moisture change is deep-seated or normal. The surface movement here is another geotech parameter, which is the expected surface movement of the soil. And this is also used in the stiffness calculations, which I'll go through later in the report. Now we have also some advanced options here, which are used for changing how the moment capacity and the stiffness calculations are carried out. First one is to do with the calculation of the concrete flexural tensile strength here. And by default, AS2070 specifies values which are based on 20 MPa concrete of 1.8 and 2.7 MPa. But if you use higher strength concrete, then these values may not be correct for your application. So we also allow users to calculate this strength in accordance with AS3600 instead, which will then feed into a different cracking moment calculated by the module. Generally, if you don't need high strength concrete for your slab, it's better to adopt the 2870 approach. Otherwise, you end up with very intense reinforcement requirements for your slab. You can also decide whether the flange slab is included in the stiffness and moment capacity calculations using this here, so either include or exclude, which will change how the moment capacity calculations are carried out. It will also affect how much of the slab mesh is considered to contribute to the section as well. So there isn't necessarily a best way to approach this, but some might yield better or worse results for your slab. In clause 4.4, there's also a criteria here for the calculation of the slab flange width in 4.4e. And this actually gives you a range of values between B plus 0.1L or B plus 1. Doesn't really tell you which one to adopt. So here we give you the option to either adopt the upper or the lower limit of the range there. The final input is just for reinforcement ductility, whether you have low or normal ductility reinforcement. And this will change the phi factor that's used in the moment capacity calculations. Okay, so now we'll run the calculations for the slab and we'll work through the items in the report here. So at the start of the report, we just have an input summary of everything we put on this tab on the left, a drawing of the slab here with the reinforcement schedule. Now, the first check we carry out is we find the classification of the soil. And this is found using table 2.3, and it's based purely on the expected surface movement provided by the geotechnical engineer. So in this case, we have a surface movement of 30 millimeters, which means we have a site classification of M. Now this classification will be modified if the expected moisture change is deep-seated, and it's changed by just adding a D suffix to the end of the classification here. And we use this later on to work out the differential deflection and the beam spacing required for the slab. Next up, the max differential deflection is calculated, and this is based on the wall construction here. So we've selected a clad frame wall construction. We've also selected to only check the limit for the deflection here. So for a clad frame construction here, it is either Ln 300 or 40, but we've only selected limit, which means we'll only take this right column here. So therefore our deflection requirement is 40 millimeters for max differential deflection. Now, as I mentioned briefly at the start of the video, the simplified method for Raft Designs has a number of limitations as to which slabs can be designed using this method. And this section of the report here checks that this slab is compliant with each of those limitations, and therefore we can use the simplified method. And the first check is to do with the maximum beam spacing, where it specifies that beam spacing should be less than 1.25 times the maximum beam spacing, which is found in figure 3.1. And that spacing in figure 3.1 is based on the site classification and the type of wall construction for this slab. Now, figure 3.1 states that for a clad frame structure with a soil classification of M, there is a maximum spacing of 6 meters, which is multiplied by 1.25 to get 7.5 meters. So we're within that both directions here. There are also limitations on beam depth, and firstly, the beam depth needs to be between 250 and 1200 millimeters for any of the beams, but you also can't have the minimum beam depth be less than 0.8 times the maximum beam depth. So you basically can't have huge variations in beam depth across the slab. So we'll check here, the minimum beam depth is 400 and the maximum is 450, so therefore that check is okay. As I said before, we also check that the loading, the applied distributor load and edge load are within the limits of clause 4.5.1, and here the limits are 10 and 25, so we're well within those limits there, so the method is applicable. Now we have some other detailing checks which we carry out too, and the first one is to do with specification of reinforcement in the beams. So often you can either select a bar reinforcement or a trench mesh here. And one of the checks that we do is to make sure that the trench mesh actually fits within the base of the beam. So if I had specified 300 millimeter wide trench mesh and a 200 millimeter wide beam, then obviously that doesn't fit. So we just check that before carrying out any capacity calculations. We also check that the slab reinforcement is sufficient, and this is just based on clause 4.5.1, and it's based on the span of the slab here. Okay, so into the capacity calculations. Firstly, we check the stiffness of the beam, and we check this in both directions, so in the x-axis and the y-axis, and this is checked using figure 4.1. And we have two graphs here. One is for the normal soil profile, and the other one is for deep-seated. And we basically link up the ratio of the expected surface movement divided by the max differential deflection, and we need to make sure that where these intersect, we have sufficient stiffness in our beams to ensure that deflection doesn't occur. So based on this ratio here, we need to have a minimum stiffness of 8.06, and we calculate the stiffness of these beams using a relatively simple formula, which calculates the second moment of area of those beams divided by the length in the span direction to log base 10. And in this case, we get a stiffness of 8.86, which is greater than 8.06, so therefore the beams have sufficient stiffness in that direction. And then we repeat that check in the other direction too, to make sure the stiffness is sufficient in both directions. And we present that here as a ratio for utilization at the end of the report. Next, we will check the strength of the beams, and the simplified method here specifies that the beams need to be reinforced so that the ultimate strength, so the section bending capacity, is 20% greater than the cracking moment capacity specified in AS 3600. And this cracking moment is calculated using the section modulus and the flexural tensile strength of the concrete, which I mentioned in the inputs. We can specify to calculate either using 3600 or AS 2870. We also need to make sure that we meet the minimum reinforcement requirements of AS 3600 as well, which are calculated here based on the size of the beam and the yield strength of the reinforcement and the flexural tensile strength of the concrete. Now in this case, we've adopted the 2870 values for the flexural tensile strength of 2.7 MPa for positive and 1.8 MPa for negative bending, and they'll be used in these calculations here. Here we have just an overview of the assumptions, which have been set by the advanced options here. So first of all, we're including the slab flange in the calculation of section modulus and minimum reinforcement, etc. We also are including compression reinforcement. This is by default in all calculations. We include the slab mesh reinforcement in the top reinforcement of the beam based on whatever the effective flange width is. And we also use the lower limit of the flange widths specified by AS2870. Now here we calculate the minimum reinforcement requirements and the minimum moment requirements for the internal and the edge beams in both directions for positive and negative bending here. And the utilization ratios that we check are the provided reinforcement compared to the minimum reinforcement and the actual moment capacity of the section compared to the minimum cracking moment capacity of the section. And you can see here that this slab is actually insufficiently reinforced for negative bending in the edge beams, and that's in both the x-axis and the y-axis there. And these outputs are reported here on the right-hand side. We also have a summary output here, which basically will return a fail if any of the checks above fail, and will give you the reason for that failure there. So it's saying it is not compliant with AS2870, and that's because we have insufficient edge beam negative moment capacity there. Now, if you need to save a copy of this report, there's two ways you can do that. You can print a PDF version here. You can also use this QR code in the bottom left. If you scan that on your phone, that will load a Quick Design web page with all these inputs preloaded. So you can share those calculations with clients or engineers or anyone else that you need to as well. And that's the introduction to the AS2870 Residential Slab Design module. If you have any questions or comments, please feel free to leave them in the comment box below. Thank you.